next speaker is Vaishnavh, who will tell us about learning the best algorithm for max cut clustering and other partitioning problems.
Right.
Hello everyone, welcome to my talk on learning the best algorithm for max cut, clustering, and other partitioning problems. This is joint work with Nina Balkan, Ellen Wittersik, and Colin White. A lot of real-world applications, you face NP-hard problems such as clustering or max cut, and naturally these problems have resulted in many different parameterized families of approximation algorithms and heuristics. And a natural question you would ask here is, which is the best algorithm according to some objective that I care about? And typically you would answer this in terms of which algorithm has the best performance on the worst case problem instance, or which algorithm has the best performance on average over all problem instances. But a more natural question to ask here, which even Rishi talked about in his previous talk, is one where you take into consideration the unknown distribution over problem instances that is defined by your application, and you evaluate your algorithms according to their performance in expectation over this distribution. So in this talk, we will consider two widely used families of algorithms, and we will show how you can learn the best algorithm from these families. So here's a quick example. Clustering is something that we face in many different domains. And in one particular domain, the kind of problem instances that you may face may involve clustering web pages by topic. And in another domain, you might want to cluster images by subject. So since it's NP-hard for most clustering objectives, there are many approximation or heuristics such as agglomerative techniques, which we will see in this talk. And the question here is, which is the best for my application? The other problem that we focus on is integer quadratic programming, which is a pretty abstract problem that applies in many different scenarios, such as max cut, SAT, and correlation clustering. And we focus on max cut in this talk, but our results apply to integer quadratic programs in general. So there are many. So typically, you would relax the integer quadratic program to a semi-definite program, and there are many ways you can round the solution output by the semi-definite program back to an integer. I'll describe this later in detail, but we show how you can learn the best way in which you can round the semi-definite program solution back to integers. So application-specific algorithm selection has been studied empirically for the past few decades in AI. And only recently, Gupta and Roughgarden proposed their learning theoretic model for this problem. And this is a very general model, and we work in this. So first, I will describe the model quickly, and then I will describe our results. So as I said, I have a family of algorithms, possibly infinitely many. And I also have a performance metric, say a cost function, which takes as input an algorithm, runs it on a problem instance I, and outputs a cost value. Besides these two, as I said, there is this unknown distribution over problem instances, which exists in nature. It tells me which sort of problems are more typical to my application. So the ideal goal here would be to pick an algorithm from this family which has the best performance and expectation over this unknown distribution. But of course, that's too ideal. So what you hope to do is you draw some problem instances from this unknown distribution, and you evaluate each algorithm over these samples, and then you pick the empirically best algorithm. So this is the protocol, and that brings us to two important questions here. The first question is, how do I ensure that this algorithm that I just picked based on the samples is also close to optimal over the whole distribution? If you think about it, this is closely tied to how many problem instances that I just sampled. If I had sampled a lot of problem instances, then I have a better idea of what the distribution looks like, and hence the performance of the algorithms on those samples will be representative of their expected performance. So this boils down to a sample complexity question. And the other question here is, given these samples, how do I find the empirically best algorithm over these samples efficiently, even if this algorithm class was infinitely large? So we'll see how this question, the sample complexity question, is answered by learning theory. In order to do that, let me define something called as cost sub A, which is basically a bunch of different functions, one function for each algorithm in my class. So each function here maps the problem instance space to the cost of running that algorithm on all the problems in this, all the problems in the problem instance space. And what learning theory tells me is that the sample complexity needed for this near optimality guarantee is proportional to how rich cost sub A is, or the intrinsic complexity of cost sub A, which is formalized as the notion of pseudo-dimension, which we'll see in the next slide. Let me know if you have any questions here. So what is the pseudo-dimension of cost sub A? Here's how I'll develop the intuition for this. So I want to know how rich this function class is. So let me pick two problem samples, I1 and I2, and let me pick a function from cost sub A. This is going to map the problem instances to cost values. Now, if I were to pick some thresholds, I will induce a labeling on these problem samples. So depending on whether the cost is lesser or greater than the threshold. Now, if I were to pick a few other functions from cost sub A, will I be able to induce every possible labeling on these samples? So this is the basic intuition behind pseudo-dimension. And more formally, the pseudo-dimension of cost sub A is a single number, which is basically the size of the largest set of problem instance samples that can be labeled in every possible way by 2 power s different algorithms in A. Like each algorithm corresponds to a function. Sure.
I mean, since the cost here, I mean, small variations of the cost may not matter, why do you choose a pseudo-dimension, not a fat shattering dimension?
We could think of using the fat shattering dimension. That's a good point. But yeah, we have focused on pseudo-dimension here. Yeah. So does anyone have any questions here? Yeah, cool. Okay, so this brings me to our main results on clustering. So as you may already know, a clustering problem instance consists of n points and the pairwise distances between them. And you want to partition these points into k sets in order to minimize a cost, such as k-means or k-median. But I will consider only an arbitrary cost for this talk, because our results apply to any such objective. Okay, I'm going to describe a rich class of clustering algorithms. Each algorithm in this class consists of 2 steps. The first step is a merge step. So I begin with all the data points in my problem instance as singleton clusters, and I'm going to iteratively merge them to build a cluster tree. So in each iteration, I pick the 2 closest clusters. I'll define what that closeness means, but I will iteratively pick 2 closest clusters and build a cluster tree. So each node in this tree is a cluster. And then I'm going to use dynamic programming to find the best pruning of this tree and output a k clustering. I'm not going to get into the details of this step, but let's focus on the first step. So there are many different ways in which I can define the distance between 2 cluster nodes. For example, one popular way is single linkage, where the distance between 2 cluster nodes is the closest pairwise distance. Or complete linkage, where it is the farthest pairwise distance. Or more generally, I can imagine an interpolation between these two, which I'll call as alpha linkage, which basically weights single linkage with a value of alpha and complete linkage with a value of 1 minus alpha. So alpha here is a parameter which defines a different notion of distance. And for each alpha, I effectively have a different algorithm in my algorithm class. And which is the best? My question now boils down to which is the best alpha in my algorithm class. And more precisely, assuming I have picked some clustering problem instances, I want to pick the empirically best alpha. Is the algorithm class clear?
So for example, average linkage is outside the scope of this family.
Exactly. So we will get to a richer class of functions later on, but just for the sake of the talk, for simplicity, I'm going to consider this. So okay, so this brings us to a key challenge here. Let's say I have a single problem instance and I vary alpha across the alpha line. Even a small variation in alpha could possibly result in completely different cluster trees. This is because, recall that in the merge step, what I indeed have is a sequence of merges, and even if one of those merges is going to change, there could be a cascade of many changes which I cannot really track. But so why is this exactly challenging? Let's just quickly contrast this with other machine learning classes, where you have a parameterized function class rather than a parameterized algorithm class. And as you vary the parameter, you expect a natural and intuitive change in the way the function is going to change. So there it's going to be easier, but for us, we don't know how the algorithm is going to run differently with changes in the parameter. But we show that we can indeed overcome this, and this is how we show. So given a set S of problem instances, we take the alpha line and we explicitly break that into polynomially many intervals. And what is special about these intervals is that within each interval, different values of alpha result in the same set of cluster trees on the samples. So when I jump from one alpha in one interval to another interval, as I said, I have no clue how these cluster trees are going to change, but I do have this guarantee that within a particular interval, they'll give me the same set of cluster trees, a fixed set of cluster trees. And here's the intuition behind why that is true. Recall that in the merge step, yeah.
You mean no matter what the input is, with this interval of alphas, you will be within this family of trees?
No, it depends on the inputs. So given a set of problem instances, I can explicitly break the range of values of alpha. So this is not a global, global partition, like independent of the inputs. Okay, so the intuition behind this is as follows. Recall the merge step, where in every iteration I effectively do something like this. I take a pair of cluster nodes A and B and another pair of cluster nodes P and Q. I look at the distance between A and B and the distance between P and Q, and I compare these distances. And depending on the outcome of this comparison, my merge step I decide what to merge in my merge step. But then let's vary alpha along the alpha line. We can in fact show something interesting, which is that there is exactly one value of alpha at which the outcome of this comparison flips. Okay? And what is more interesting is that that particular value of alpha is the solution to this equation, which is in fact defined purely by 8 points, which are namely the closest and the farthest points in A and B and P and Q. So now if I simply iterate over all sets of 8 points in my cluster instance, I can mark such alpha values on the alpha line, and thereby I'll partition the whole alpha line into n power 8 different intervals. And what is special about these intervals? Within each alpha interval, I have a fixed outcome for any potential comparisons that I'll make. So the moment I fix all of them, I'm also fixing the cluster tree that will be output for any alpha in those intervals. Does that make sense? Okay. So we can similarly extend this to S different samples and say that there are like so many intervals, such that you have a fixed set of trees, which also means I have a fixed set of prune solutions and a fixed set of costs, which brings us to our pseudo-dimension bounds. Okay. What we show is that the pseudo-dimension of cos sub A is in fact theta of log n. Okay. The upper bound follows from this very nice property that we just proved. So recall that if I have as many samples as the pseudo-dimension of cos sub A, I should be able to pick 2 power s different alpha values, each inducing a different labeling on the samples. But indeed, I have just shown that even if how many ever alphas I pick, these are the number of behaviors that I can expect from those alphas for a fixed set of problem instances S. So that results in this inequality, which gives me an upper bound on the pseudo dimension.
Can you remind us what is the cost of clustering that you're using here?
So as I said, that's an abstract cost. It could be k-means or k-means or distance to ground truth clustering. Okay. So as far as the lower bound is concerned, it's a very intricate analysis where we carefully construct log n different clustering instances that can be labeled in every possible way by different values of alpha along the alpha line. Okay. So now to find the best alpha for a given set of clustering instances, we only need to, first of all, draw log n different clustering instances. That follows from the pseudo-dimension bound. And we show how you can solve for these polynomially many intervals for that set of problem instances. And then we only need to run the algorithm for 1 alpha per interval, because all the alphas result in the same expected, same empirical average cost on the set of problem instances that you have sampled. Then you can, it's straightforward to find the empirically best interval of alphas. Okay, so so we also prove more general results.
So maybe
Sure.
a question about, so what this might give is that really there's not just one best interval for alpha, there might be many.
Yeah, there might be many, and any of them are going to be
So
equally
some
good.
are good on some inputs and some are good on other inputs. Let's say that there are two. The input is really. So in practice, then what do you do? After you learn this alpha, it's not that there's one alpha value that you really want to learn. Run it on. Maybe there are 10, and you want to take the best of the 10.
Um,
Like,
so is your question that I could use different alphas on different problem instances?
yeah.
Okay, if
So
I
you restrict yourself like to proper learning, where that again, like you're not allowed at the end to say, okay, I learned that in fact the best thing for me to do, which gives me results which are twice as good, is to run once with alpha equal 1/3 and once with alpha equals 2/3, and take the best of the two, and that's much better than any one of them alone. You're not allowed to do that.
Yeah, so here we pick a single alpha, and I can see that it could be possible to do something like this, where I pick multiple different alphas, maybe depending on what the problem instance looks like. And even Rishi has some results where they actually find a mapping from parts of the problem instance space to alpha values. And so I guess that sort of answers your question. So, yeah.
It seems worth pointing out that in the AI literature, that problem is called algorithm selection.
Yeah.
And the problem that you're looking at is called algorithm configuration, because you're trying to find one configuration of the sort of parameterized space of the algorithm to commit to once and for all.
Yeah, that's a good point. Yeah.
Which isn't an argument against this, but it does seem terminologically complicated.
Okay. So this is a straightforward, efficient, computationally efficient, and sample efficient algorithm selection method. So we have more general results where we also consider a nonlinear interpolation between single, complete, and average linkage. Earlier, we only had a linear interpolation between those two, and we prove a pseudo-dimension bound of theta of n. Of course, because this is a richer class of algorithms. So we have another set of general results, which is motivated by the following fact. If my cost function was something like k-means or k-median, I can as well use that in my pruning step as my DP objective. But if it was something like distance to the ground truth clustering, where these ground truth clusterings are provided only for the training problem instances, and I cannot legally use them in my algorithm itself, I should only use a proxy objective in my pruning step. So what we consider is a much richer class of algorithms where I not only parameterize the merge step with many popular algorithms, many popular linkage procedures, I also parameterize the pruning step with many widely used kinds of DP objectives, and we prove pseudo-dimension bounds for this. Yeah, sure.
But we have results that show that there are cases for which no agglomerative algorithm, no hierarchical clustering will give you a good approximation to the optimal k-means solution.
Okay, so
Because we are still within the family of linkage algorithms.
yeah, that's true.
And there are results that show that there is a limit to how well can linkage algorithms approximate the optimum of k-means or some other objective.
True. So what I am doing here is competing with what is the best in that class. And so even given that class, how do I know which is the best to use? Let's say I'm limited by that class. But yeah, I can see that there are limitations to the class that I've just chosen. Okay, so that brings us to the end, to my results on on clustering. So going to MaxCut. So as you all know, in MaxCut, you are given a graph G of n vertices and edge weights. And your aim is to partition the set of vertices into 2. In other words, you want to assign -1 or +1 values to these vertices. And here you have a particular quadratic objective. So unlike in the case of clustering, where I considered an abstract or an arbitrary cost, here I have a particular quadratic objective, which is nothing but the total edge weight connecting the partition that you just created, as shown in the figure there. Okay, so our results apply to integer quadratic programs, more general integer quadratic programs, but as I said, I'll focus on MaxCut in this talk. Okay, so here's how, so how am I doing on time?
Have another 20 minutes.
So here's how how people popularly solve these problems. You have this integer quadratic program, which is which is hard to solve. So they relaxed that into a semi-definite program. So I'm not going to get into the details of this SDP, but all that you need to know is that I find vector assignments for the vertices instead of integer assignments, which means I'm going to embed these points on an n-dimensional unit sphere, where n is the number of vertices in the graph. And now, in order to bring that back to a graph cut solution, I need to round it. And the richness in this method comes from the fact that I could potentially use different rounding methods. And there's no one rounding method that is clearly going to be the best for my application. So which is the best rounding method for my application? So we consider a family of SDP rounding techniques that was proposed by Feige and Langberg. So each rounding technique in this family is a randomized rounding technique. In fact, there are two steps, and both of them are randomized. So as I said, there is this embedding of points that you can arrive at by taking the problem instance and applying the SDP. Now, all you do is you choose a random hyperplane in this embedded space, this n-dimensional space. So once you pick the random hyperplane, what I'm going to do is I'm going to assign plus or minus 1 values to these embedded vertices in a random fashion. But then the probability with which I assign them to plus 1 or minus 1 is dictated by how far these vertices are from the hyperplane. So if a vertex is very close to the hyperplane, I'm not really sure whether they belong to plus 1 or minus 1. So with roughly equal probability, I assign them to one of them. So if they are very far away from the hyperplane, my probability is going to be skewed to either plus 1 or minus 1. So more formally, in order to do this, I need what is known as a rounding function, which maps distances from the hyperplane to probability values. So in particular, they present this popular class of rounding functions called the S-linear rounding functions, which so these are a bunch of different rounding functions, and each function in this class is a piecewise linear function. There are 3 pieces, with the middle piece being parameterized by the parameter s, as you can see over there. Okay, so does anyone have any questions here? Okay, cool. So, okay, but here's one thing that I have to talk about, which is that since each algorithm here is randomized, how do I assign a performance value for each algorithm in this class? So each algorithm, in fact, results in a distribution over performance values depending on your random hyperplane draws and this random assignment that you do over here. So what you typically do is you look at the expected objective achieved by each algorithm. So I want to pick the S with the best expected objective. So more formally, recall that I want to bound something that looks like this, obj sub A, which is in fact a bunch of different functions, one function for each algorithm in my class, and each algorithm is defined by a parameter S, which is the parameter of the rounding function. So each function here maps the problem instance space on the x-axis to expected objective values achieved by that particular value of S. So let's look at this more carefully. Your expected objective achieved by a value of S on a problem instance is in fact an expectation over the random hyperplane draws, which is the outer expectation. And inside you have another expectation, which is an expectation over the random assignments that you do based on the rounding function. But fortunately, that has a closed form expression. So given the rounding function and given the hyperplane, which are inputs, so you have S and the hyperplane and I, the problem instance, I have a closed form expression. But what I actually care about here is the full term, that is obj of S comma I, which turns out to be difficult to handle because there is an expectation over hyperplane in the n-dimensional space. So how do we overcome this? So let's consider something similar to obj sub A, which is obj star sub A. So just like obj sub A, I now have obj star functions in this class. So for each value of S, I have an obj star. So the function here maps the problem instance space and the hyperplane space to an expected cost value. So for a fixed value of S, it maps a problem instance and a hyperplane that I've picked to an expected cost value. It's still an expectation because it's an expectation over the random assignments that I do. But the good thing is that this has a closed form expression. Okay, so what we show is that the pseudo dimension of obj sub A, which is what we actually care about because it gives us the sample complexity guarantee, is in fact upper bounded by the pseudo dimension of obj star sub A. Okay, so why is that good for us? Because we know what obj star looks like in each of these, and we can hope to bound the pseudo dimension of this latter quantity. And we in fact show a bound on that, which directly implies an upper bound on the sample complexity. So let's look at our bound, which is the following. So we show that for this class of algorithms defined by the S-linear rounding functions, the pseudo dimension of obj star sub A is theta of log n. Again, we prove a tight bound. See, upper bound follows from the following fact. As I said, obj star has a closed form expression, which in fact looks like this. Here, phi s is the S-linear rounding function, parameterized by the value s. I is the problem instance, which defines the xi values, which are the embedded points in the n-dimensional sphere. And h is the hyperplane that I've just picked after the random hyperplane picking step. Okay. So if you look at this, it turns out that it is, in fact, a piecewise quadratic or linear function in S. So if I have this line of S values, and as I can partition that line into pieces, into at most n plus 1 pieces, where n is the number of vertices in the graph, and each piece is a quadratic or a linear piece. Okay, why is that interesting? Recall that in order to talk about pseudo-dimension bounds, I pick these thresholds for each problem instance, and then I see how different values of S induce different labelings on the problem instance with respect to a particular threshold. In fact, over here, if I were to pick a threshold like this, it's going to partition S into n many intervals such that within each interval, the labeling for all the S values in that interval is fixed, as you can see over here. Okay, so again, now this, like how I prove the pseudo-dimension bound for clustering, I can do something similar. If capital S, which is the set of samples, is as large as a pseudo-dimension, then I hope that if I pick 2 power S, I can pick 2 power capital S different values of the parameter S, which give me different labelings of the sample set. But at the same time, now I know that there is this, there is only so many different values of the parameter S that induce different labelings. So using this inequality, I get an upper bound on the pseudo-dimension. Similar, like how we did for the case of clustering, we also have a lower bound on the pseudo-dimension, for which we have this careful construction of log n different input instances. But now the input instance is not just a max-cut problem instance, but it's also a hyperplane. It's a max-cut problem and a hyperplane instance. Does anyone have any questions here? Okay, cool. So now that I've established that you can be sample efficient, all I need to do in order to find the best S on a set of samples is the following. You only need to draw log n different problem instance samples, because that's the pseudo-dimension, and that ensures near optimality. And for each instance, I'm going to draw a single random hyperplane. Okay, and so recall that the expected cost of a particular value of S is in fact an expectation of many hyperplane draws, infinitely many hyperplane draws, but we only need to draw a single random hyperplane. And then we need to, we can write down the empirical average of obj star as a function of S. This is a closed form expression, as I told you already, and this has only polynomially many intervals, and each interval is a linear or a quadratic interval. Has a linear or quadratic empirical average. And we can then find the best S within each interval and efficiently find the globally best S. Now so we prove identical results for, in fact, more general classes of rounding functions. So for example, it can be a sigmoid-like rounding function, which is parameterized by a single parameter, and we show that the pseudo-dimension of obj sub A is theta of log n. And we also present computationally efficient algorithm selection procedures for this class of rounding functions. So this brings me to the end of my talk. So in summary, our work contributes to analysis of algorithms because we provide theoretical grounding to application-specific algorithm selection. And we also push the boundaries of learning theory because the algorithms that we consider, the function classes that we consider, correspond to algorithms that are significantly complex, multi-stage, and also randomized. So we also nail down the intrinsic complexity of these algorithms by providing both upper and lower bounds on the pseudo-dimension of these classes. And what is surprising, as was pointed out in the previous talk, is that these are tight bounds which are super constant, despite the fact that the algorithm class themselves have only constantly many parameters. To end my talk with a couple of future directions, can we generalize our SDP rounding analysis to more rounding functions and to more SDP-based problems? And another question is, the kind of algorithms that we have considered can be run efficiently in practice. But what if there are algorithms, like SAT solvers maybe, which run pretty slow, which take a long time, and hence to actually compute the empirical performance of those algorithms, it's impossible to actually run them to completion. So in such a case, how do we handle this problem, and how do we provide theoretical guarantees? So those are the future directions, and that's it. Yeah. Thanks. If you have any questions, please feel free.
Well, quite a bit of time. So.
It seems to me that in your first application, you ended up with 2 parameters, right?
Yeah.
And it was impressive to see how this works. I'm curious, I mean, practical algorithm configuration settings often have dozens of them, right? So
yeah.
Do you think it's relatively straightforward to expand your analysis to cases like this?
It should be, I mean, it depends on the problem, but it should be possible. Like even Rishi had in his model, they even discuss multiple parameter algorithm families. So similarly, it should be possible to split up the space of parameters into these grids, within each of which the algorithm has almost similar behavior. But I can see that it depends on the algorithm class that you are considering, whether that's easy to do or not. Yeah.
Okay.
That's it.
Yeah. Any other questions? Well, Kevin. Okay, so let's thank the speaker again.